Let's get going. This is my little recursion joke here. All right. Yay, someone laughed. So to start, I want to do a little exercise with you. So let's play a game. Two people play. First person gets the same number from 1 to 10. The next person gets to add 1 to 10 to that. And then you go back to the first person, they got to add 1 to 10 to that number. And the first person that says 50 wins. Okay? So play that with a partner, like 2 or 3 times. You get it? So if someone says a number between 1 to 10,
okay, so
you add 1 to 10 to it.
And then you add 1 to 10 to it. And then I add 1 to 10 to that. The first one of us that can say a number at or above 50 wins. So I start at 6. You say, I'll say 19. I'll say,
Okay, who won? You won. You're the only winner? No one else won? Hey, so when did you know that you were going to win?
The beginning.
The beginning?
I knew I was going to win at the beginning.
How did you know you were going to win at the beginning?
Because, well, a person can only say a number from 1 to 10, or higher into another number. So then you just subtract so you go one number above 11, and then you subtract 11 times 4 from 50, 44, so it's 6. And then you can keep saying 6, and then add 11 to that, 17, because you'll always have, I don't know.
All right. You're right. That's someone else that won. When did you know you were going to win? Besides the beginning. Or you suddenly was like, I'm going to win.
So we realized the first time around, so the first person that they can say 39 obligates the other person to say something that will make it so they can win. And then it was a battle, okay, how can I force somebody to say something at 30 so then I can say 39? Or
Right, so you kind of work backwards. So your goal is to hit 50, which means the other person had to be in what range for you to be able to say 50? Obviously not 50, right?
that'd be 40.
So 49 at most, because you can add 1 to that. And then 40, because if it's lower than 40, you couldn't add more than 10, so you couldn't get to 50. So you want them to be in this range for that to be true. For them to be in that range, you should be in what range? Well, it has to be 1 lower than that, right? Am I off now already? Let's go to my slide.
If you get to 39, you obligate them to say.
Yeah, you want to, that's right, you don't have a range, you have a specific thing you want to say. So you want to be 39, and then they're going to be 38 to 29. And then for that to work, you want to be 29, which means they should be 18 instead of 27, which means you want to be 17, which means they have to say something in that range, which means you start at 6. So if you get to start playing the game, also 4 times 11 somehow, yeah. If you start the game and you say 6, then you're guaranteed to win, right? So why did I have you play this game? Yeah, it's sort of a recursive kind of thing going on here. There's, you know, it all you you go down the layers to get to the answer here. And yeah, like the first time you do it, you sort of start realizing around 30 or something. You're like, oh, things are important now, you better pay attention, right? But once you realize that, then you realize that there's another layer before that you can get to that's important as well, and then a layer before that, a layer before that, a layer before that. So this is the kind of thinking that is important for recursive kind of applications. And the good thing is, in some ways, you don't have to kind of work through 1,000 layers of this yourself. You let the computer do that, but you have to understand that process, that if you can kind of peel it back, peel it back, you get to some kind of actual answer finally. Okay? So you can go win some money by betting people that you can say 50 first, you know, and start with 6 and you'll safe every time. Okay? So.
Assuming that you follow this.
Yeah. So remember we talked about recursion last time, and the two important things in recursion is you have that base case where the recursion stops and gives a specific value back, and then a reduction step that progresses the recursion towards that base case. And in some ways, if you can see the relationship between those two things, you've really solved the problem, right? You've solved the essence of the problem if you can do that. So we had some sort of silly things with recursion, like adding up a list of numbers we already know how to do, and looking at the Fibonacci sequence, which has some mathematical interest, but not a lot of real practical kind of interest. So let's look at another application of recursion. So you're familiar with your file system on your computer, and at the beginning of the semester we talked a little bit about paths, where we're talking about going down folders and getting to specific locations on your hard drive. But typically there's basically two things on your hard drive, right? There's files, and Java, and there's folders. And even packages are actually folders on the file system. And maybe we want to do things that ask questions about this file system, right? We want to count things up or find things in there. And it's sort of hard to think of that as a loop because you go down to this folder, you want to dive into that folder, look around, come back, and look down to the next folder. Oh, there's a file now. And it gets kind of complicated if you sort of think about it in sort of a serial array kind of style. So we want to think about this recursively. So Java has some nice things to help us do this. It has the file class that we've used to read files before and write files. You can also, if you have a file that you've opened up, you can ask, is it a file? And so it returns true or false. And notice this uses also that nice is something terminology I was trying to push a couple of lectures ago, where if you're going to return true or false, then make it be like a little question. And it's either a file, or if it's not a file, what is it? There are only two things we can be on here, file or something else. A folder. And a folder is filled with more files and other folders, right? So using these things, and then one more thing we can do is that if it is a folder, we can ask what is in the folder and get a list of files. And here when it says list files, it's list of capital F file, not like text files. Like the files can also be folders, right? So when I say list files, it means list everything that's in that folder, files and folders. So we can use these two things to kind of explore our file system a little bit. So let's do a simple one. Let's count the number of files and folders, let's say, the number of things in a folder. Okay, so for example, I have a folder I made here. I can't seem to make this bigger. CS1410 test. And in here I have little tiny a.text, b.text in another folder, and c.text in another folder with stuff in it, and another folder with some stuff in it, right? So a very simple little file system I have here, and maybe we want to do something like count up how many things are in here. All right? So what's the base case here? So we're doing some sort of recursive thing. When can I count something?
If file dot is file equals true.
So if it is a file, and I mean that in the sense of a actual file, like a document of some kind. That's a base case because we can't go into that file, right? We can't get deeper into the file system there.
Just to clarify really fast, if it's lowercase f, that's a file. If it's uppercase f, it could be a folder or a file.
Well, capital F is a class in Java that knows about folders and files. This is just my word, a file. Okay. A base case has a value. What's the base case here? Value. So it's a file. What do we do? What is that worth? 1. We're trying to count them, right? So that's 1. If it's not a file, in other words, it's a folder, we want to get the list of files and do what with it?
Same thing for each other.
We want to count how many in each. Right? So this is the recursive part, because this whole thing counts how many things are in a folder. And it's either a file, or we want to count up how many things are in there. So let's give this a try. All right, so count files and folders. And we're going to take in a file F, some starting location. And in this case, I'm going to start it in that little test case folder I made, CS1410 test, that had that ABC kind of stuff in there, and see what's in there. And so to write this recursively, we're going to write the base case. And I'm going to check to see if the base case condition is met. So usually that base case has an if statement, right? If count, if number equals 0, or something is some low kind of value. And in this case, if the file F is a file, then what do we want to do? What's the answer? Let's say I passed in this thing that was a file. I want to give an answer at that point, right? It is a file. So I'm going to return 1, because we're counting up 1 file in this case. So I pass it a.text, that's a file, and I say, okay, my answer is 1, because that's all it is. If it's not a file, then it is a folder, folder. And in here, we need to get that list of files from the folder and count up how many things are in each of those, including themselves, right? So I'm going to do a little for loop for file, I'm going to say, and we're going to use this nice notation, list files. All right, so what's going on here? This thing, remember, gives me really an array. I'm going to make a note here. Really a file array from list files. Right? So this call says, give me all the files that are in the folder. And I'm going to iterate through them one at a time, assigning each file to this variable here so we can do something with it. Okay? Yeah.
If we try and call that function on a file that is actually a single file, will it just return that single file, or will we get an error?
I don't know what the behavior is for list files on an actual file. Something. But we've already handled that case up here, right? And we can look it up. All right, so if we list the files, then what do I want to do? I can get a count here for the number of files in that file, but I want to accumulate that now and count up all the things that are in that folder. So I need some sort of accumulation kind of deal here. Int total files. Okay, it's going back to some Python there. 0. So now we're doing a basic loop, an accumulation loop. I'm going to count up all the things that I've found in this folder. If they were all files, I would just say add 1 every time through this loop, right? But there may be a folder inside this list, in which case I want to get all the values out of that thing. So I'm going to say total is adding up the count files and folders of file. And I'm on total files. So this dives down and counts them all up. actually, I want to count the current folder I'm in as well, so I'm going to make that a 1 there. And when I'm done counting them up, I need to return that value. Total files I keep. All right, so that's all there is to this, which doesn't seem like enough, right? That's the whole thing about recursion always. It's like, it doesn't seem like you've done enough code somehow. So if it's a file, return 1. Otherwise, count up all the files and folders that are in the current folder using the same method I've defined here. And every time it hits a file, it's going to return 1, right? And accumulate that total and return it. So maybe let's look at a case where I have a folder, and in it I have a.text. So let's run through this by hand and kind of see what the behavior of this would be, right? So I am here. Is that a file? No. So it goes in the else statement. And we have our total is 1. And then it says count up all the files. So there's a list of files, and it's going to call count files and folders on this particular file here. It goes back into the method up here, and file F is now this file, right? Both of these things still exist on the stack under the same name F, but this is the one it knows about at this current time, this scope. And it says, is this a file? It is a file. So this says return 1. So this thing turns into a 1. And that says then, we're back up in this case, and it says add 1 to this, we get 2, and then we return 2, and we're done. Okay? So it only recursed once in this case to get into this folder and figure out how many things were in here. But it worked, right? Now if I run this on my test case, count 12. And if I look, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things in that whole series of stuff. Okay, so it dives in, counts 1, and says, how much is this worth? Well, that's going to be worth like 9 or something like that, because it goes down to here and says, it's 1 plus whatever things are in here, 1, 2, 3, so that was 3 plus 1 is 4, plus those 2, you know, so on. It just keeps diving down until it comes back up and tells you the answer. Oops, wrong code. Now, it's the kind of thing, I don't know. Like I said, it almost seems too easy. When you write it, you just have to kind of trust what's going on in some sense. You know, what's the answer? Well, it's 1 if it's a file. Otherwise, I'm going to count them all up using the same code here, and eventually I'll get to the right answer, right? You just have to kind of, I don't know. It's hard to force yourself to write this recursive code, I think. You just have to kind of write it out real fast and then see if it works. Questions on that, though? You need to get in the mindset of this stuff. It takes a little effort to kind of think it through. I think it's harder to confirm in your mind that it works than write it in the first place in some ways. You just sort of write it and it works and it's good. All right, let's try a different one. Let's see. Also, let's first of all, I think I can. Let's see. Let's try to see a little more what's going on in this thing. So I'm going to say where I'm in, and f dot file name. I'm in the wrong language. How do I get? I want to get the file get name. Okay, yeah. So this will tell me where I am in the process. And if I run it again, okay, I'm in CS1410 test. It then checks in that directory is A, B, and folder 1. So it goes some reverse order here. Looks at B, looks at A, looks at folder 1. In folder 1 is, where's folder 2? Oh, found folder 2. And inside folder 2 were E and D. And these things, anyways, you can kind of track where it's recursing as it goes through that pile of stuff, right? I think that helps understand some of that as well.
Why is it counting the folders as well?
Counting what?
The folders?
Because I started here when it's a folder, I said I'm going to count that as the 1 right there. All right? And that's a choice. I can skip the folders, right? And then I just make that a 0, and it would count just the files.
The name of the method says it.
What's that?
The name of the method says it.
Yeah, count files and folders. All right. Questions, though? I want you guys to kind of think about these issues here, because these are good ways to think about solving these problems. All right? So let's try another one. Let's get the size of the largest file. So files take up space on your hard drive, and they're usually listed. Like if I go and look at my files, it says it's a plain text file that's 0 bytes. There's nothing in that file. That's why it's 0. This one is 0 bytes. All right, I didn't work too hard to put stuff in there. This one is 10 bytes, and it says hi there. Okay, so that one has some value. That's going to be our target. We want to find this giant file with 10 bytes taking space on my hard drive, right? So I want to find the maximum file size. And there is an f.length that gives you the file size. The number of bytes, I guess, yeah. What's the base case for the maximum file size? What's that? 0. Well, I'm not saying, when do you know you're at a base case, right?
I was going to say, wouldn't the base case be like the first file you...
Or really, the base case is, the way to think of this, if you call this method with a very simple case, when can you actually give it an answer, right? So if I want to say the maximum of all the files and folders in a folder or file, when can you give an answer to that without doing any more work?
Once you have a file?
Yeah, so if I say max of a.text, what's the maximum of this thing? It's the length of that, right? So the base case is you have a file and you just say the maximum is that length. Okay? If it's not a file, then what's the maximum? So it's a folder, right?
How many A.dot lengths are in there?
Well, this file's like 10, B is gonna be length 1,000,000, C is like 55 or something like that. Each file has a value of some kind, right? So how can we? What would you say is if it's a folder? What's the maximum then?
Is it sum of the inner lengths?
It's not a sum. We're trying to find a maximum, right? Like the biggest one of these. So let's say there's a.text, b.text, and folder 2. Which one of these has the biggest length file in it? Is it A? Is it B? Or is it whatever's in here? It's the max of any of those, right? So the case is either it's one file, or we have to search through them all and find the maximum. We know how to find the maximum in a loop kind of thing, right? So let's give this a try. Get this down a little bit. All right, so evil positioning there. All right, so if f is a file, so the base case really for all these file ones is like it's a file. That should be the little lesson from this. If it's a file, then we return f dot length. Because the maximum of one thing is that thing itself. If I said, what's the maximum of 2? You'd be like, it's 2, right? So again, there's no like genius move required here. It's just sort of believing that that's really the answer I want to hear, right? So otherwise, we want to do a maximization, an optimization loop here, right? We want to go through and figure out which thing is the biggest that's in this folder, because now we're in the folder, in a folder. So to do an optimization loop, we need to somehow start off by saying our largest so far. And when we do optimization loops, I often say take the first thing that you find and initialize your loop that way. But we already know that file sizes go from 0 to some big number. And so saying largest so far of -1 is safe in this case, right?
Why don't we just do 0?
Well, yeah, but maybe you want to say where that largest thing is, and then you'd have to do some extra work for that. So we're saying that we're going to find the biggest. We know it's going to be bigger than -1, and so we're going to start off at -1. And now we're going to go through our files, and I'll do the same thing. So angry at me there. F.list files. So again, remember that returns an array of files that are in the folder, and I'm going to iterate over them one at a time, store them in file, and do something with it. And I'm going to say that the largest so far is the maximum. So I'm going to use the built-in max instead of doing my own thing. If this number is bigger than this thing, then save this thing, kind of thing. Max. The largest so far that I've found, or the largest file size of the thing I'm on, which is either a file or a folder. So I'm recursing here in this comparison. Complaining. Do I need to import this? Oh, so I made this be a long for some reason. Oh, okay. So long is a big int, right? And this length thing wants to return a long, so I'm going to turn everything into a long here. And then it should work. Okay. All right, so I'm saying if it's a file, the maximum is the length of itself. Otherwise, it's the maximum of what I know about so far versus all the other things in this folder. And to count up any file that might be in this folder, I have to recurse into it and count up which is the maximum thing in there. And if that has a folder, I need to count up the maximum thing in there. But it all happens just by saying I want to pick the biggest of what I know so far versus the biggest of what's left in this file system, like going down the folder chain here. And it all works nicely, and then I can return largest so far. Okay. And if I run that, biggest file size, max file size is the, what do I call this thing? Largest file size. Largest file size. And that was about it. So if I run it, tiny, okay. Max file size was 10 bytes, and that's true. I think it was 0 except for when it was 10 bytes. All right, so we can do things besides just count things up, right? We can do comparisons in here. And again, I think these are hard to do unless you force yourself to write some of these. And then you kind of pick your way along. Okay, I need a base case. And then I need the rest of it. what is that rest of the thing? And if you just have to, you have to learn how to summarize the answer rather than try to get yourself into the details. Your instinct's going to be like, oh, go through the files, and then like, if file is file, do something else with that directory. Your instinct is going to want to be unrolling this recursion in the code yourself, and you're going to get caught in sort of an infinite loop here, where then, okay, loop over files, and then if it's a file, you know, do something else, loop over files, and you know, you don't get caught trying to solve the problem yourself in some ways. You're giving the relationship between, what do I need to kill here? Okay, is that right? You're giving the relationship between the beginning and sort of like the succinct answer of what the rest of the answer is, right? What's the most brief, abstract thing you can say that somehow solves the problem for you? And it's a beautiful thing when you can come up with that, but otherwise, you're just sort of casting around trying to write code that somehow encompasses this. And it's usually very simple. You just have to kind of believe it. So anyway, think about that. Let's try one more example. You all seem so excited about that. We're going to make some pictures. All right, so most of you have heard of fractals before, probably. So a fractal is a geometric object that has self-similar properties. In other words, if you look at the details of it, it looks like the whole thing. All right, so it's made up of smaller copies of itself, typically. This is an example. It's kind of hard to see here, but this is the Mandelbrot set, which is a famous fractal. And the thing about it is, if you zoom in, you'll see more things that look like this sort of hidden inside this picture. All right, so there's people that get very entranced with this and, you know, screensaver kind of stuff, and think they're going to find like God at the bottom of the fractal or something like that, right? So it's a sort of infinite series of stuff. We're going to make a fractal using what's called turtle graphics. So turtle graphics are sort of a classic way of doing some introductory programming based back in the 70s with this logo language. And basically, you have a thing, the turtle, and you say, go forward, turn left, turn right, and you try to make shapes, right? So, and it drags a pen behind it, and sometimes they had actual physical instantiations of this, like little robots that did this, and sometimes it was all on the computer drawing lines. And so to draw a square, for example, you'd say, turtle, step forward, turtle, turn left 90 degrees, turtle, step forward, turtle, turn left 90 degrees, turtle, step forward, turn left 90 degrees, turtle, step forward, right? So you're breaking down these actions into steps, and it helps people kind of understand the sort of step-by-step nature of computer programming a little bit. So we're going to use this to make a snowflake. Hey, wait, where is it? My last page. I'm like frozen here now, too. Who has done? Okay, that's weird. All right. So this famous snowflake, and you look at this design, and you'll be like, wow, that looks like something hard to figure out how to draw, right? Because of the details. And this thing is really built up by finding a perimeter. Like you take a triangle, and for each side of the triangle, you add another triangle on it, and for each triangle side of that, you add another triangle on it. And if you're going to try to solve this in sort of a, if you think of it the wrong way, you're going to try to find some nice equation that says, okay, given this triangle, where does this triangle live? And then let's add some more triangles on the side of that. And there's some, you know, sine and cosine thing you can derive here. And it's going to be tricky to kind of figure out how to do this properly. But if you think about it recursively, it actually gets pretty easy. So a basic side is you draw a segment, you draw a triangle, and you draw another segment, right? And that would make sort of the beginning outline of like this shape here. To get the fractal part, how do you draw this line? That's the question, right? And if you look at it, this segment has another triangle built on it, right? So I can say, don't just draw a straight line here, draw this thing scaled down to fit here. So I divide this into thirds, and I draw a triangle line. To draw this side, what do I draw? I want to draw a thing that has a triangle line. So notice it's this base shape of a line with a triangle bump in the middle. And anytime we want to draw a straight line, we don't draw a straight line, and instead we draw a thing with a bump on it. So we keep breaking down our things to have sides on it. All right? Now where do we stop? The true snowflake doesn't stop. It's infinite. You go forever doing this process, right? One weird thing about this snowflake, in fact, is that every time you add a layer of bumps, you're getting the length of the perimeter like 30% longer, right? And if you do that forever, you have like an actual infinite length boundary here, but it encloses a fixed area.
Isn't it always going to cut into thirds though, so it's going to get like infinitesimally small?
Yeah, they get smaller and smaller, but if you take the series of that, I think it still goes unbounded.
Okay.
So let's write code to do this, all right? Let's see. So first of all, we're going to use this turtle class. And the turtle knows about its position and the angle it's headed. And then it has some stuff to turn, some stuff to go forward. And when it goes forward, it draws a line behind it. And you can set colors and all sorts of stuff. If I were to run this, there's a little test code. So it basically makes a turtle and then says go forward, go left, go forward, go left, go forward, go left. If I run this, nothing happened. Maybe I remember that happening. Okay, let's just, I'm pretty sure this will work, so let's just go ahead and try this. All right, so we're going to make a turtle in our snowflake class. And I'm not using that anymore, I think. We set up how big the window is going to be, 600 by 600. We start the turtle in a certain spot. And then we say, draw me one of these things of this size, okay? So to draw one of these things, we need a base case, and we need and so actually let me say one more thing. So when you draw this thing here, that's called the sort of the 0th layer of subdivision, right? Each time we go down more detail, we're adding another layer of subdivision. When we, and maybe that's 1 because maybe this makes it a layer. When we add this bump, that's an n equals 1 layer. So the more layers we want, we're going to specify this n, and that tells us how to, we don't want to go forever because it'll take forever, right? We don't actually go to infinity ourselves. We want to just sort of just do some approximation of the snowflake. Yeah.
What do you do when the pixel distance between the triangles goes to 0?
Yeah, so that's, we should stop, right? There's no point in drawing more at that point. So we have this n that's we're going to keep track of kind of what size part of this we're working on right now. Is it the big one, or the 1 subdivision, or 2 subdivisions, or 3 subdivisions? And we're going to say if n equals 0, then we're going to want to actually draw something. So we're going to turtle, go forward, side length. Side length. Okay. Oh, it's lowercase side. So at a certain point, we got to draw something. And the base case is we've kind of counted down the layers, and we're going to actually try to draw a side here. If it's not the bottom layer, then we want to draw a smaller version of ourselves in that space that fits there. All right? So we're going to say, we're going to draw one of our snowflake sides, and it's called this Coke snowflake kind of thing. So we want to go down a layer, so we're going to draw a smaller layer, a smaller copy of ourselves, and we're going to take our side length divided by 3, and I gotta make that an integer. So what we're saying here is, in order to draw one of these sides, we want to draw a smaller version of ourselves in that same space. Okay? And we do that by first drawing this part, and then we turn left 60 degrees. And then we draw another copy of ourselves. And then we turn back. So if we go this way, we turn left 60. We come up here. We really want to turn right some amount, which is the same as turning left a negative amount. So I'm going to say turn left minus 120. And then draw it again. Turn left 60, and that's all there is to it. So let's try running this. I did a negative turn left, which doesn't seem better to me, but that's what I did before. So
Is turtle not capable of turning right?
oh, we never did our final line. Why? Oh yeah, I need one more line. I think it is, but it's not what I had, so I'm not risking anything right now. I need one more drawing at the end here. Oops. So there are four segments in it, right? 1, 2, 3, 4. I only did 3. So run it again. All right. So what happens is we said n was 1. It's not 0. We call n minus 1, which is 0, on a third of the length. It recursed. N was 0, and it went forward. Then we turned left, and then we did a n minus 1, 0. So it did this part, go forward, turn, right?
So if we did a call on this with the side length and we just said 0, it would just draw a straight line for us.
If I said this,
0, we just have a line.
it would just be a line. Right? So the first subdivision,
So technically,
n of 1, it adds one layer of bumps to it.
So what the way you have it described there, n equals 1, would really be?
Yeah, not wrong.
Okay.
So let's try 2. So it said to draw this line, we're going to want to draw something subdivided like that, but each one of those things is subdivided into one more bumpy thing as well, right? So 3, oops. What did I do there? Getting kind of nice. Let's try 5. Now to make the full snowflake, you then rotate 120 degrees or something and draw another side, and then rotate and draw another side. Because we're only drawing like the top part of the triangle, and really there's 3 sides to that base triangle. 6. Notice it's now taking, each time takes longer, right? Because in order to draw, it's drawing 3 times as many lines here.
I don't know if it's not you, because you have more.
I don't know. Should still appear.
I wonder if 6 is a point where the pixel it gets so small that it actually is not.
So it's rounded down to 0.
Yeah.
But then it should just still recurse, and but maybe the go forward fails or something if you give it a 0 length or something here. Let's try one more time just in case there's some funny thing going on. Henry never tried past 5. Let's just enjoy 5 then, shall we? So notice, again, this problem, while it was sort of hard to actually set up recursively, it's not so hard if you see it sort of in action. I think it would be really hard to do this in some sort of non-recursive fashion. You'd be keeping track of how long your sides are and where you are. You know, none of these are sort of canonical 60-degree turns. They've all kind of gotten very, very different. But it says here, if we're ready to draw a line, draw a line. If we're not ready to draw a line, break it into something that looks like that, and draw that. But it may also require each of those pieces to be drawn with a lumpy bit as well. Okay, so that's really it. Ponder these issues. You know, you'll reach some greater awareness if it starts to make sense. But recursive stuff is always sort of fleeting. Like it works, and then you're like, how does that work? You have to kind of hold on to it.